Guys, today we're going to talk about measuring segments. We're really going to talk about constructing segments in the classroom. That's something you really want to practice hands-on as much as possible. There are some directions for constructions in your textbook, and you can use those if you want, but really, we're just going to talk about measuring segments today, especially when you have information that's given, not necessarily just using a ruler. I think most of you probably know how to use a ruler, and be sure that when you do use a ruler that you know and are familiar with measuring with centimeters and millimeters, or measuring with inches and fractions of an inch. And if you're not sure, then we can talk about it in class a little bit. So some of your essential questions are like, what kind of information do you need to calculate a measurement, and what's an appropriate unit of measure? This is a good little question about measuring a fish and making sure that it's within the range for you to keep it, as opposed to tossing it back. So you may want to pause the video, read through that, and just make sure you understand that question a little bit. So there's a postulate called the ruler postulate, such that every point on a line can be paired with a real number. This makes a one-to-one correspondence between points on a line and a number. So you can see here that the lowercase letters are the numbers that correspond to the points right up here, point A and point B, that are on that line. And most of you are pretty familiar with the number line. So to calculate the length of a segment, you can take the absolute value of the difference between the coordinate of point A and the coordinate of point B. So for example, we're going to say that we want to find the length of segment ST. And this is the symbol for finding the length of a segment. So if you don't see a bar on top, that's called the length of segment ST. So most of you would probably just say, well, that's a really basic number line. I'm just going to count it. Notice that this number line is counting by 2. So make sure if you're just going to like hop it like a bunny and count it, that you might go 2, 4, 6, 8, 10, 12. So the length of ST is equal to 12. That's not such a big deal when you can count it pretty easily. So make sure that you pause the video for just a sec. Make sure you can find the length of UV and also the length of SV. So when we talk about those two letters together without a little bar on top, then we're talking about the length of a segment, and we need a numerical value for that as much as possible. So the length of UV, if you notice, is a length of 4, and the length of SV is going to be, sorry, S to T was 12 units, and then we went another 6. So that's going to be 18 units, right? All right. So moving on, let's talk about other ways that we might measure segments. One of the critical ideas in geometry is the segment addition postulate. I've seen segment addition postulate in every single geometry book I've ever worked with, including a book from the 1800s that talked about segment addition postulate. So there are some ideas in geometry that have very specific names that any geometry teacher or a student well versed in geometry would understand, and then there are other things that we don't necessarily give specific name to. But if we have 3 points A, B, and C, and they're all on the same line, all on the same line, such that B is between A and C, then the length of AB plus the length of BC is equal to the length of the whole segment AC. And I like to say that the sum of the parts, right, that would be AB plus BC, is equal to the whole, which is AC. And I know that you've done that with fractions a lot of times. You've put fractions together to get one whole piece. It's the same as if you were putting sticks end to end and then measuring them with a measuring tape. So let's talk about applying the segment addition postulate. And the way that I'm going to ask you to do that is by actually taking a look at this problem. You've got a picture here with segment EG split up into 2 smaller segments, segment EF and segment FG. Notice that all 3 points are on the same line segment, and you have some information about the length of EF and some information about the length of FG, but these are algebraic expressions. They're not solid numbers, and we want to talk about taking information that's off on the side of the problem, like this. The length of EG is 59, so we're going to put that here. The length of EG is 59 units, whatever units, centimeters, millimeters, miles, could be anything. We don't know what the unit of measurement is. And we want to find out what's the length of EF and what's the length of FG. So what I've done here is kind of split it up so that you could actually talk about solving the problem on the left And then this is going to be your justifications. And the reason why I did this is a lot of times you'll see reasons in your textbook for why you do certain steps or why you write a specific equation. And one of the biggest problems with geometry is that unlike algebra, in algebra, oftentimes you're given an equation and you're told to solve this. And if you've learned different ways to solve, then you know what to do. In geometry, you're not told what equation to write. And you have to come up with that based on the relationships that you observe in a picture. So when I observe the relationships in this picture, what I notice is I notice that the length of EF and the length of FG make up the whole entire segment EG. So if I'm going to apply the segment addition postulate in words, then I would say in symbols, excuse me, I would say in symbols, the length of EF plus the length of FG is equal to the length of EG. Got it? And then what I've done here is I've taken the information from the picture. For EF, the length was 8x minus 14. And for FG, the length was 4x plus 1. And we know that we were given that the length of EG was 59. So I essentially just substituted in the information. So we're just going to say that I use substitution. And what I'm really trying to do here is kind of get you ready for chapter 2 way in advance. So justifying what we're doing is a good idea. And so now we're going to just combine like terms. Since we're adding, you know that we can drop the parentheses and we can just combine like terms. So 8x and 4x are like terms. We get 12x. Negative 14 and a positive 1 are going to give us minus 13 equals 59. So all I did there was combine like terms. Some people call this like a closure property when you're simplifying things, but I would prefer just that you call it combining like terms. And then on the next line, you notice what happened. How did I get from here to here? What was different there? Notice that if we add 13 here and if we add 13 here, that's how we get the 72. So what we used there was the addition property of equality. So I'm just going to say addition. And then you can tell I'm trying to give you a hint right here by dividing both sides by 12 that 72 divided by 12 is x equals 6. And then notice that the very next question says, are we finished working this problem? So you always want to go back, and I'll do this to you a lot. You often will have to solve an equation, but when you solve an equation and get a value for a variable, you're not necessarily done with the problem. Notice that up here I was asking you to find the length of EF and FG. So we're not quite done yet. No, we need to know what is EF and what is FG, right? Okay. Well, EF was given to us as 8x minus 14. So EF is equal to 8x minus 14, which is 8. Sub in the value you got for x, which was 6, minus 14. So that's 48 minus 14, which is going to be 34, right? So the length of EF is 34. And now let's find the length of FG, which was given to us as 4x plus 12. You can go back and look at the picture again if you can't see it up there. So 4 times 6 plus 1 gives us 25. 24 and 1 is 25. So the length of FG is 25. And that's pretty much how you would set up any problem where you could use segment addition postulate. It's always a good idea to write it as an addition problem. The sum of the parts is equal to the whole. The two little pieces end to end is equal to the big long one. So it's a good idea at this point for you to take a chance, take an opportunity to pause the video and see if you can figure out what's the length of JK and KL. And I'm going to go ahead and work it out. If we write it in symbols first and apply the segment addition postulate, then in symbols, the length of JK plus the length of KL is equal to the length of JL. Then I'm going to plug in everything that I know. So I'm going to say JK is 4x plus 6. Where did I get that? I got that from the picture. Plus KL is 7x plus 15. Also got that from the picture. Equals JL. Where is that information? I don't see that. Ah, here it is. Here's where that information is, right here. JL is 120. So I probably should have put that in my picture so that I could know where to find that information. There we go. All right, so like terms, I'm going to combine like terms. 4x and 7x is 11x. And then 6 plus 15, that's going to be 21, is equal to 120. And then 11x is equal to 99. want to subtract 21, and x is equal to 9. Are we done? We think we're done. Not really done. Remember, we were supposed to find jk, and we were supposed to find kl. So jk is equal to 4 times 9 plus 6. So that's going to be 36 plus 6, which is 42. We found the length of jk, and kl is going to be 7 times 9 plus 15, which is 63 plus 15, which is going to be 78. The other thing that you can do is when you find your values, make sure it works. Remember that you were told that the length of JL was equal to 120. So you should go ahead and check, is 42 plus 78, does that equal 120? So is that the same thing? Yes. Okay, if you go ahead and add it, you can just check your work a little bit. That's always a good idea to do. Okay? All right. Last thing we're going to talk about today, we're going to talk about congruent segments. Congruent segments are segments that have the same length or same measure. In a diagram, you're either going to see a number between, kind of somewhere in the middle between the segments a little bit. And if there is a number and it's the same number, then those segments have the same length. If there's no number, then you might look for these congruent markings. We call them tick marks or hatch marks or whatever you prefer to say. Those can be used to indicate that segments are congruent. So if I draw, let's say I draw another segment, here's one, and if I want one that is congruent to it, then I would just make a copy of it, right? And so if I want to show that these two segments are congruent, I can put a tick mark on this one and a tick mark on this one without having any idea what the actual length of them are, and that would be how I can indicate to you that they are congruent. Without having that information or without having numbers, that we can't make any assumptions about segments being congruent. In symbols, we would say that if the length of AB is equal to the length of CD, then segment AB is congruent to segment CD. So if you're familiar with logic, or sometimes you might see that symbol in a Spanish class. In a logic class, you call that little tilde right there. That's what you put over top of an equal sign to indicate that segments are congruent or that angles are congruent. In Spanish, I think it's called an enye, but I'm not positive about that. And then you say if the length of AB is equal to the length of CD, then segment AB is congruent to segment CD. Notice that in this situation, there are no bars on top. When we talk about length, no bars, right? No bars on top. So hats off, and then hats on when we talk about congruence, okay? When you talk about symbols, be very careful about that. When you talk about length, you don't put a bar on top. When you want to say that lengths are equal, or when you want to give a numerical value for length, you don't put a bar on top. When you want to identify congruent segments, you put a bar on top. All right, so let's find some congruent segments. We want to know segment AC and segment BD are congruent. So what do we want to do? We want to find the length of AC. What is the length of AC? Well, the length of AC is 2, 4, oops, one more. We're just going 1, 5. So the length of AC is 5, and the length of BD, we're going to go back. I'm going to go backwards. 2, 4, 6, and then one more. BD is equal to, oh, I didn't do AC right. Messed up big time. Sorry, guys. Let's back up. Hold the phone here. You may want to just ignore that altogether. All right, the length of AC, didn't go far enough. 2, 4, 6, and then one more right there to 5. So the length of AC is equal to 7. And the length of BD, I'm going to go backwards. 2, 4, 6, and one more right there. And the length of BD is also equal to 7. So yes, segment AC is congruent to segment BD. Got it? So make sure the lengths are the same. So now we want to know, you should pause again, make sure, can you find out, is segment AB congruent to segment DE? So check your measurements a little bit. And in this diagram, the length of AB. So let's talk about 3A. It's a good idea to pause, do it on your own, and that would be the length of AB is equal to 5, and the length of DE is equal to 4. So that's no. AB, segment AB is not congruent, and I'll just make a congruent sign with a slash symbol, is not congruent to segment DE. And then in 3B, to find the length of AC, suppose you subtract -2 from 5, do you get the same result? So for 3B, we want to know if we subtract -2. So what this means is from 5, if we say 5 minus -2, do we get the same result for the length of AC? So if we do 5 minus -2, that would become 5 plus 2, and the length of AC would be equal to 7, so that's yes. Okay, remember that you can find the length of a segment using the absolute value of the difference between those two. So I'm going to go right back to the very first page, right here, where you had a number line. And you were finding the length of a segment on a number line, and it was real easy to just make hops, right? But suppose, let's try something a little bit different. Suppose point A has coordinate -312, and point B has coordinate 567, right? Well, you would not draw a number line with all of those things, and we want to know what is the length of segment AB, right? We want to know what's the length of segment AB. So suppose we want to do that. You're not going to draw a number line and do little bunny hops and count all the way, which is a good reason why we would do the absolute value of the difference between the coordinates. So does it matter which one comes first? That's kind of a good question. So let's find out. So if we say -312 minus 567, right? Is that the same? Let's find out. Is that the same? Let's figure out what the value is first. First, let's just find the value. Okay, so that would give us absolute value of -879, which would be 879, right? Fine. Okay, great. But what if we did the absolute value? Now I'm just going to come over here and say the absolute value of 567 minus -312. Does that give us the same exact thing? Sure, of course it does. It just makes it positive a lot faster. So the length of AB is still going to be absolute value. It just turns positive fast now. So that's the value in seeing why would you maybe take the absolute value of the difference between the coordinates instead of just counting on a number line. That's it. That's all we got.